Hello students, welcome to EPG Pathshala. I am Dr. Vishwanath Tiwari from Central University of Rajasthan. Today I am going to talk about a module that is mechanism of enzyme action, activation energy, collision and transition state theories. This module has been taken from paper Molecular Enzymology and Protein Engineering. So what is the objective of this module? The objective of this module is to understand the mechanism of enzyme action. We will also discuss what is the role of activation energy in enzyme function. We will also discuss what is the assumption of different model that is given for enzyme catalysis or enzyme action. We will also discuss what is the limitation of different models that is given to explain enzyme process. So this module is divided into following section. The first we will discuss about basics of enzyme. Then we will discuss about activation energy and its role in enzyme catalysis. Then we will discuss about different theories that is used for enzyme catalysis. The first theory we will discuss about the collision theory. The second theory we will discuss about transition state theory. We will also discuss the limitation of these theories. So first, what is enzymes? So enzymes are the biocatalyst that has efficiency, a specificity and have a mode of regulation. So what is substrate? Because enzyme converts substrate into the product. So what is substrate? So substrate is chemical species that is modified in a chemical reaction and responsible for the formation of the product. The rate of conversion of substrate into the product is slow. Why it is slow? Because of existence of thermodynamic and kinetic barrier that is present when a reactant is converted into the product. So what is contribution of an enzyme in the reaction? So enzymatic reaction can be increased up to 10 to the power 17 folds. So when reactant is converted into the product, we have a formation of state that is known as transition state. So transition state is observed during any chemical reaction, but it is having the highest free energy. But if it having highest free energy, it is going to be unstable. So it has highest energy and minimum stability. So what is activation energy? As you know, activation energy is energy that is required for any reaction to proceed. And you know that there is a barrier existing between reactant and product, and that barrier is going to be promoted, is going to be maintained because of existence of transition state. So therefore you can redefine your activation energy as energy difference between substrate and transition state. So most of the reaction are slow because substrate doesn't have sufficient energy to cross activation energy barrier or transition state barrier. So how enzymes are involved in crossing this transition state barrier, we will discuss in this module. We will also discuss how your efficiency of an enzyme is explained by collision theory, which is stating that rate of reaction is directly proportional to effective collision. So how your effective collision is influencing the efficiency of the enzyme, we will discuss. We will also discuss how your transition state theory is used to explain a specificity of your enzyme. So in this module, we will discuss the catalytic mechanism of the enzyme and different theories that is given to study the enzyme catalysis process. Now we will discuss what is activation energy and what is the role of activation energy in the enzyme catalysis. So, activation energy is a term introduced in 1889 by Swedish scientist Arrhenius to describe minimum energy that must be available to a chemical system with potential reactant to result in a chemical reaction. The activation energy may also be defined as minimum energy required to start a chemical reaction, or if you see the transition state, then it is a minimum energy difference between reactant and most unstable transition state. Activation energy of a reaction is usually denoted by EA, and it has a unit of kilojoule per mole or kilocalorie per mole, and it is defined by Arrhenius equation, which is K is equals to A e to the power minus EA upon RT, where K is a reaction rate constant or reaction rate coefficient, which is equals to Vmax by ET when you're talking about a enzymatic reaction, and A is a product of collision frequency and fraction of the molecule with enough kinetic energy which causes a reaction to occur with the likelihood of a molecule with sufficient kinetic energy will collide and causing reaction to occur. Or in simple way you can say number of collision per second which occur with the proper orientation to react. EA is activation energy of the reaction, T is a temperature in Kelvin, R is a gas constant, and E to the power minus EA upon RT is a probability that a given collision will result into a reaction. The Arrhenius equation is converted into linear form, and that form will be log K is equals to minus EA upon 2.3 R into 1 upon T plus log A. Therefore, a plot of log K or log Vmax by ET, because I have told that K, which is a catalytic constant, is equals to Vmax by ET versus 1 by ET. So, a plot of log K or log Vmax by ET versus 1 by T yield EA, that is activation energy for catalytic steps. One more thing, that is activation energy calculated from Arrhenius plot will be apparent or average value. There is another form of Arrhenius equation, and that is integrated form, and the equation become log K2 upon K1 is equals to EA upon 2.3 R in the bracket T2 minus T1 divided by T2 into T1, where K2 and K1 are specific reaction rate constants, and T2 and T1 respectively is the condition of temperature at which these rate constants are calculated. The Arrhenius equation can be transformed into the another equation which directly calculate activation energy, and that is derived from integrated equation. So the final equation will be EA is equals to 2.3 R into T2 upon T1 divided by T2 minus T1 into log K2 divided by K1. There are two theories that is given to explain the process of enzyme catalysis. The first theory is collision theory, that is proposed by Strauss and Lewis, which is based on collision between reactant molecules. The second theory is transition state theory, which is proposed by Earings, Evenus, L. and Polanyi. And this theory is based on formation of transition state during the conversion of reactant into the product. So we will discuss each theory one by one. We will also discuss the significances and limitation of different theory. The first theory is collision theory. So collision theory is based on kinetic theory and assume a collision between reactant before a reaction can take place. So collision theory basically states for a biomolecular reaction to occur, molecule must collide with one another to initiate the reaction and collision with sufficient amount of the energy and collide in a proper orientation. So the important thing is collision with sufficient energy and proper orientation. So collision theory is an aspect of kinetic molecular theory, and it is strongly interconnected to the chemical kinetics. This theory is used to explain how different variable affects the rate of reaction. These theories have an idea that the reactant particle must collide for a reaction to occur, but only a small percentage of total collision have appropriate energies and orientation to effectively cause reactant to form into the product. In order for a molecule to react, the Arrhenius explained that the colliding molecule must having enough kinetic energy to overcome the repulsive and bonding forces of the reactant, and this minimum amount of energy that is required for a chemical reaction to occur is known as activation energy. Higher the activation energy of a reactant, smaller the amount of energetically collision present, and therefore slower the reaction. Energetic collision are the collision between the molecules which have enough kinetic energy to cause a reactant to convert it into the product. The second thing is, not all collision are energetic collision because they do not provide necessary amount of activation energy, so that all collision leads conversion of reactant into the product. So in other words, you can say that if activation energy is large, only few energetic collision take place and most of the collision are non-energetic. So we have slow reaction. While in contrast to it, if activation energy is lower, then more and more energetic collision take place. So the reaction is faster. So in this way, if enzymes are involved in the reaction, they will alter this effective collision or energetic collision. A reaction cannot occur if a substrate does not collide with activation energy of the reaction. If atoms collide with less energy, atoms simply bounce back away from each other. The only collision with the energy that is equals or greater to the activation energy will cause a reaction, will create a reaction. Ultimately, the chemical reaction involve breaking up the some bonds or making few bonds. When we are having activation energy is the key for initiating the bonds breakdown, and when collision is too gentle, then adequate amount of energy is not brought to the bond, then reaction fail. Therefore, the activation energy is very crucial in the reaction rate, because depending on how much kinetic energy we have that is used in the collision, the reaction will vary in its speed and its frequency. Therefore, we can say that collision theory states that rate of reaction is directly proportional to the effective or energetic collision, and effective and energetic collision is dependent on how a reactant molecule collide with each other, how the bond formation and breakdown take place within the reactant molecule. So along with the significances of the collision theory, there is also some limitation of this theory. An important criticism that this theory have is that the colliding molecule must have sufficient energy to overcome a potential energy barrier to react. That means if a reactant is not having that potential energy barrier, or a molecule doesn't have sufficient energy to overcome this energy barrier, then reaction fail. So how your reactant molecule is converted to the product, they are not explaining, because every time some reactant molecule is converted to the product. So this is a criticism, but with the development of collision theory, with the development of study of enzyme kinetics, this theory is outcome with the different assumptions, different corrections made by different scientists. So you can say that according to the collision theory, the rate of product formation is directly proportional to the effective collision. Why effective collision? Because all the collision that is taking place is not going to be effective, or they are not going to form product. So the collision which is forming the product is known as effective collision. So the rate of reaction is only dependent on effective collision rather than total collision. And the maximum collision that can take place in any reacting system is known as diffusion limit or catalytic perfection. But you know that all the enzyme or any other reaction or any other catalyst, they all are not having catalytic perfection. So we never achieve the diffusion limit, but if you have enzyme, then it will have more effective collision. For example, the maximum diffusion limit which is present have the order of 10 to the power 9 per mole per second, and an enzyme which is well known for its catalytic efficiency, and that is catalase. Catalase enzyme have efficiency constant. Efficiency constant is explained by kcat by km of the enzyme. So the catalase enzyme has efficiency constant of 3.6 into 10 to the power 7. If you see here, it is 3.6 into 10 to the power 7, and maximum diffusion limit is 10 to the power 9. So you can see how close it is. So therefore you can say that enzyme increases efficiency of a catalytic reaction. Then how your enzyme is increasing efficiency of the reaction? That is because presence of active site. So we have active site where the substrate bind, and then collision taking place between the substrate or reactant. And in the presence of active site, that creates such an environment which makes most of the collision that is taking place in the active site effective. So therefore you can say that the presence of active site in the enzyme increases the efficacy of catalytic reaction, and that is explained by collision theory. After discussion of first model, that is collision theory or collision model, the second model that is given for catalysis is transition state theory. So transition state theory is also known as activated complex theory or absolute rate theory or theory of absolute reaction rates. Transition state theory suggests that a reactant molecule approaches each other so closely so that they will form a less stable state either or as compared to reactant or product. For a bimolecular reaction, a transition state is formed when two molecules' old bonds are weakened and new bonds are begun. The new bonds begin to form while old bonds are broken down. It will leads to a different type of binding pattern in the substrate, and that will leads to the transition state. The theory suggests that a reactant molecule approaches each other so closely that a transition state is formed which is having highest energy. The potential energy of the system increases at this point because approaching reactant molecule must overcome the mutual repulsive forces between outer cell electron of their atoms. So atom must be separated from each other as the bond are broken. This increase in potential energy corresponds to an energy barrier over which the reactant molecule must pass if the reaction is to proceed. The transition state occurs at the maximum of its energy barrier, and transition state is an unstable combination of reactant molecule that occur at the potential energy maximum. The combination can either go to form the product or fall apart to return the unchanged reactant. The energy difference between reactant and potential energy maximum state, that is transition state, is referred as activation energy. As you can see in the graph, a reactant molecule is converted into a transition state and transition state going back into the product. And you can see there is an energy difference between reactant and transition state. So a reactant molecule must cross that transition state to be converted into the product. But because the reactant is not having so much energy, so only few reactant is converted into the product because of this transition state barrier. But when enzyme or catalyst are come into the picture, they altering the energy of the transition state and finally making more and more reactant molecule to cross the transition state barrier, and that will lead to the formation of the product. So therefore, enzyme and catalyst are initiating the reaction by interfering with the transition state. So what is the basic idea behind transition state theory? The first basic idea is the rate of reaction can be studied by examining activated complexes that lies near to the transition state point. Transition state point is also known as saddle point. So transition state or saddle points have a potential energy surface. So the details of how an transition state or enzyme transition state complex are formed is not important, but what is important is how your transition state is stabilized, how the transition state is converted into the product. The second basic idea is activated complex are in a special equilibrium that is known as quasi-equilibrium with the reactant molecule. The third basic idea about transition state theory is, so the activated complexes that are converted into the product and kinetic theories that can be used to calculate the rate of this conversion. So these three basic ideas are behind the transition state theory. After discussing the transition state theory, let's have discuss the limitation of transition state theory. So transition state theory have following limitation. The first limitation is when applied to each elementary step of a multi-step reaction, the theory assumes that each intermediate is long-lived enough to reach the Boltzmann distribution of energies before continuing to next step. But when the intermediate are very short-lived, then transition state theory fails. In such cases, the movement of reaction trajectories from reactant to intermediate can carry forward to affect the product selectivity. Therefore, the first is a intermediate which is short-lived, these theories fail. The second point, a second limitation of this theory is transition state theory is also based on the assumption that atomic nuclei behaves according to classical mechanics, and it is assumed that unless atom or molecule collide with enough energy to form transition state, then the reaction doesn't occur. However, according to quantum mechanics, for any barrier with a finite amount of energy, with a defined amount of energy, there is a possibility that particle can still tunnel across the barrier. With respect to chemical reaction, this means that there is a chance that a molecule will react even if they don't have collide with enough energy to traverse the energy barrier, to cross the energy barrier. While this effect is expected to be negligible for the reaction with large activation energy, it become a more important phenomena of reaction with relatively less energy barrier, since the tunneling probability increases with increasing barrier heights. The third limitation of this model is transition state theory fails for some reaction at high temperature, because this theory assumes that reaction system will pass over the lowest energy transition state or saddle point on the potential energy surface. While this description is consistent for reaction occurring at relatively low temperature, at high temperature the molecule populated higher energy vibrational modes, their motion become more complex, and collision may lead to transition state far away from lowest energy saddle points. This deviation from transition state theory is when observed even in the single exchange reaction between diatomic hydrogen and hydrogen radical. After discussing the theories of transition state, its limitation, let's have discussed the significance of transition theory for enzyme catalysis. So each catalytic event requires minimum of 3 or more steps, all of which occur within few milliseconds, that characterizes typical enzymatic reaction. So according to transition state theory, the smallest fraction of catalytic cycle is spent in most important step, that is a transition state. Pauli proposed that powerful catalytic action of enzyme could be explained by a specific tight binding towards transition state species. According to transition state theory, the rate of reaction is proportional to the fraction of reactant in the transition state complex. Wolfenstein hypothesized that the rate increase imposed by enzyme is proportional to the affinity of enzyme for transition state structure relative to its Michaelis complex, that is enzyme substrate complex. That means they are proposing that the affinity between enzyme and transition state is relatively more important than affinity between enzyme and substrate. So because enzyme typically increase the non-catalytic reaction by a factor of 10 to the power 14 to 15, and Michaelis complex have dissociation constant in the range of 10 to the power minus 3 to 10 to the power minus 6 molar. And it is proposed that transition state complex have the dissociation constant in the range of 10 to the power minus 14 to 10 to the power minus 23 moles. As the substrate progresses from Michaelis complex to the product, the chemistry occur by enzyme-induced changes in electron distribution in the substrate. The enzyme alter the electronic structure by protonation, proton abstraction, electron transfer, geometric distortion, hydrophobic partitioning, and interaction with Lewis acid and bases. They are accomplished by sequential conformation changes in enzyme and substrate, and with a combination of individual weak forces that are brought to bear on the substrate, and the summation of individual energies result into the large force capable to relocating bonding electron to cause bond breaking and its formation. Analogs that resembles the transition state structure should provide the most powerful non-covalent interaction known, even if the only small fraction of transition state energy is captured. The transition state for chemical reaction are proposed to have lifetime near 10 to the power minus 13 second, on the order of time of a single bond vibration. Enzyme function to stabilize transition state lying between reactant and product, and they would therefore be expected to bind strongly any inhibitor that closely resembles with the transition state. The substrate and the product often participate in several enzyme reactions, whereas transition state tend to be characteristic of a particular enzyme. Hence, if you are designing an inhibitor against the transition state, it is going to be more specific for an enzyme as compared to the inhibitor that is analogous to the substrate, because transition state is unique for an enzyme. So, the identification of numerous transition state inhibitors supports the transition state stabilization hypothesis for enzymatic catalysis. Currently, there is a number of enzymes known to interact with transition state analog, most of which has been designed with the intention of inhibiting the target enzyme. Such examples include HIB1 proteases, racemases, beta-lactamases, metalloproteases, cyclooxygenases, and many other examples, which is for which we have a transition state analogs. So students, let's summarize what we have learned in this module. So in this module, first we have learned what is enzyme. So we have learned enzyme are biocatalyst that has a efficiency, a specificity, and have mode of regulation. We have learned what is collision theory, what is transition state theory. We have learned how the collision that is taking place within the reactant or between the reactant are responsible for product formation. We have also discussed what is diffusion limit. So we have discussed that any molecule which is converted into the product is going to collide with each other, and the maximum collision that is possible is known as diffusion limit. And we have learned how the effective collision, the collision which is taking place in a proper orientation, is responsible for converting reactant into the product. So according to collision theory, the rate of product formation is directly proportional to effective collision that is taking place between reactant and other molecules which is involved in the product formation. So we have discussed the second theory, that is transition state theory. where we have discussed the existence of transition state. So, transition state is a highest energy state which is formed during conversion of reactant into the product, and transition state barrier is important for reactant to convert into the product. So, if transition state barrier have energy which is very high, then your reaction is slow. So, enzyme facilitating the reaction by two ways. The one way is they are increasing the energy of reactant by producing binding energy. What is binding energy? So, binding energy is a energy which is produced when your reactant bind to the active site. So, binding energy will help your reactant to cross the transition state barrier. At the same time, enzyme stabilizing the transition state and decreasing the energy of transition state. So, enzyme decreasing the energy of transition state, that making the activation energy lower. So, there is two ways how your enzyme facilitate the reaction according to transition state theory. The first one is by increasing the effective energy of substrate, or by decreasing the activation energy of transition state, or activation energy of the reaction. We have also discussed what is the limitation of collision theory, what is the limitation of transition state theory, and we have also discussed what is the significances of these theory in enzyme catalysis. We have also discussed how activation energy can be calculated and determined using Arrhenius equation. So, we have discussed how your efficiency or specificity of enzyme catalyzed reaction is explained by collision theory and transition state theory respectively. We have also compared at the required places how your enzyme is different from the catalyst. So, in this way we have learned that when an enzyme is involved in the reaction, it facilitates the conversion of reactant to the product by making collision between the reactant favorable. So, we will have more effective collision. By producing the binding energy, it will basically help your reactant molecule to have effectively more energy, which will help to cross its transition state barrier. It will also explain that enzyme stabilizes the transition state, so it will decreases the energy of transition state, so it's making reaction more favorable. So, in this way we have learned how your enzyme is participating in the reaction, and how your collision theory, transition theory and Arrhenius equation is helping to understand the process of enzyme catalysis and its mechanism. Thank you.